everybody. I am doing this one at school, so you'll hear the hum of the fan, but it's a little too hot to turn it off. All right, so here we are. I'm not sure what day this is going to be, so I'm going to go ahead and get a video. I imagine it will be Monday. All right, so that would be March 6th. Solutions and mixtures of compounds such as salt and water. So, solutions are mixtures. You know how we talk about compounds, atoms, and then there's mixtures of compounds and atoms, or mixtures of compounds, or mixtures of elements. But most of the things that we know and use in the world are complex mixtures. All right, so let's see what this has to say, and you'll find a lot familiar here. Solutions are mixtures of compounds such as salt, NaCl, and water, H2O. Both are made of two or more atoms. Homogeneous or homogeneous solutions in water are mixtures. All the solute is whatever the compound is we're using, dissolves, like salt, and we can't see the compound particles anymore after we stir it up. And the other common one, of course, is sugar. Homogeneous means it looks like only one thing, and that's water. All right? So, here's an example. We'll make it really big. So, really common, the solvent is the water. Solvent. The solute is the sugar or salt or whatever it is that you are putting in. I thought this looked like potassium iodide, which is yellowish, and it dissolves well. All right, but what you see is that there are all these things that we can't see in the water, and the reason we can't see them is there's no clumps of them anymore, no crystals. They're all have been separated into individuals. That's the reason we can't see them, because an individual particle is ridiculously small, right? Now let's look at a familiar. This pretty much describes our life, especially the things we eat. The mixture of Coca-Cola is a solution. It contains syrupy ingredients, yet we know that there's a proprietary mix. Proprietary means that, they don't tell anybody the recipe. But it's a mixture of syrupy ingredients that makes it very sweet. Water, there's food coloring in there to make it just the right color. And then at the end, they put in carbonation by pushing in CO2 gas. Now, it's homogeneous. That is, we only see one thing. But then when they put in the carbonation, now we can see the bubbles separately. And so then it looks heterogeneous, meaning we can see two different things, heterogeneous. But most of the solutions that we are talking about look all the same, just as Coke does without the bubbles. You've probably drunk Coke that the bubbles have gone into the atmosphere, right? Yes, so that would be a homogeneous mixture because the carbonation is gone. All right, so here's our essential question. Really, what is a homogeneous mixture that we can use the idea, applying the idea? What is the most common solvent when making a solution? What is a solute in the solution? What do the water particles do when an ionic compound is dropped into water? And when does dissociation into ions happen to an ionic compound? All right, so one of the reasons that I think this is so important, other than that I'm an analytical chemist, and what an analytical chemist does is see what's in the mixture and how much of each thing. The reason this is so important is for environmental considerations, and it's environmental water, environmental air. So we do all sorts of tests to see what's in these solutions. Air is also a solution of pollutants, oxygen, nitrogen, argon, CO2, and then any sort of air pollution is in there as well. So air is a mixture. All right, in addition, our body is a solution inside. Each cell is a solution. All right, and it's surrounded by the membrane. Our blood is a solution. Some of it's homogeneous in that you can't see it, but red blood cells do show up, don't they? Yes. So blood itself, when it comes out of a person, is it looks very red, and it looks as though it's just one thing. But whenever blood sits, we know it clots. So eventually the fact that you can see multiple things in blood appears. All right, so those are the reasons, physiological reasons why solutions are important. Air pollution, water pollution, environmental things of all. So think of that latest chemical spill out of a tank car. It was nitric acid in Ohio. All right, so they're having to measure all kinds of things that nitric acid might have done when it met in the environment. So nitric acid is a good solvent. So it picks up all kinds of things. All right. So solutions made with water are called aqueous, or we can call them aqueous, abbreviated AQ. So this comes from, in English we call it water, right? But in Spanish you call it agua. Spanish comes from Latin, and in Latin it's aqua. So aqueous comes from the Latin version of agua, and so words that are connected to it are like aquarium. The color aqua is the blue of water. There's so many words that start with aqua, all right? So if you want to call this aqueous, you may. Yes, since agua is a much more familiar term to us than aqua is. So let's look at the properties of homogeneous or homogeneous solution mixtures. The solvent is most often water because water is ubiquitous. Ubiquitous means everywhere, whether it's salt water, whether it's lake water, whether it's river water, whether it's tap water. These are all solutions because things are dissolved in them. All right, so the solvent is often water in the natural world. It's almost always water when we cook as well, with the exception of sometimes we use oil. All right, the solute must be a soluble compound and is often crystalline, as shown in the first image. So see how this thing right here is a geometric figure, all right? Yeah, so these things all combine, and the crystal itself would have the shape that I draw, and you would see millions of these crystals under the microscope. I should say millions of particles in the crystals under the microscope, since particles are so small. Thank you. The crystal is broken down in this case, and that's what we're going to look at when dissolving occurs. The water particles, when dissolving occurs, surround the compound particles as shown with sodium chloride. And the ions it is made of are surrounded by water particles. So we can't see separate clumps or crystals anymore, so it looks like there's nothing in the container but salt water. It looks just like water until we taste it and realize it's salt water. Or sugar water. It looks just like water until we taste it. All right, so here's the crystal, our crystal of NaCl. And you can see how, all right, I'm showing you more of the dimension. So these are all packed together in a very uniform shape. And of course, when you put it in the water, all of these water particles are present, correct? But look what they do. They immediately start coming over to attack the crystal. So this is a violent story. So the water molecules keep attacking the crystal, and they break it apart. And look what they do. So here with chlorine, the negative one, all right, the water molecules are oriented so that the hydrogens here, the positive end, is towards the negative end here. No, up's fine, thanks. So each one is surrounded. And look, 1, 2, 3, 4, 5, 6. There's even 7 here. All right, that's amazing. So this is called hydration, right? I have to say that chloride ion is highly hydrated when it's surrounded by 7 water molecules. So he has been taken hostage. But the same thing has happened to sodium, only it's still the water particles, but look at this. It's weird. This time, the water has oriented itself so the oxygen ends are near the positive ion. All right, so this has a partial negative charge, and we'll look at that in a second. So when water comes and attacks, the oxygen ends attack the positive sodium crystals. The hydrogen ends attack and go after the chloride ions. All right, and then look what happens. At the end, we can see that these are surrounded by the ring of water. Surrounded by a ring of water. So you can see why we couldn't see one single ion. All we see is water because he's too small to see. He's way too small. Now, this sign right here means partial. And we indicated that it's not an ion. It's a partial negative charge. So not an ion. And when we get to covalent bonding, we will talk about these partial charges. Not an ion. Only a partial charge. It's not anything like a +1 or a -1. Only a partial. It's a fractional charge. All right? And the same thing happens with sodium. So it's the slightly negative oxygens attracted to the sodium cation. So remember a cation? Remember my drawing and how skilled I am? This guy looks a little horsey, doesn't he? All right, but then, all right, so a cation, all right, is a positive ion. Positive ion. A negative ion is called an anion, but it's not as fun a word. All right. So this is what's happening in when you dissolve something. When you dissolve something, it becomes solvated. All right, solvated. I know there's so many terms. All right, so let's watch this video, and if it doesn't work, actually, I don't think this will work. I think you'll have to watch this video on your own, because for you to get points, you'll have to do that. All right, so let's skip that for now. So what is inside the solution that we can't see when it's made with ionic compounds? What's inside? That's the question. The solvent is distilled water. All right, when I make a solution, I always use distilled water because I want pure water. And the solute is the compound such as sodium chloride that we will dissolve. And you notice that ionic compounds break into their ions. That's what we'll be seeing. So let's go ahead and let me show you that. All right, so when the crystal breaks down, what we have is individual sodium ions and individual chloride ions, and of course we have millions of these opposite ions. Millions. All right, I'm just going to show you what's in the compound. So we have one sodium ion and one chloride ion in the compound. So that's what happens. Ionic compounds in water break up into ions. And when a compound breaks apart into ions in water, this is called dissociation. So in the compound, sodium and chlorine were associated, right? Sodium and chlorine were associated. But when they get into water, they dissociate. They move apart. All right, so associated colleagues. All right. Now they're dissociated from each other. All right, so associate means come together. Just like the teachers, all the teachers work together. All right, as colleagues, we're associated with this science department at Mesa High. All right, dissociate would mean that somebody would leave, or we would break apart as a department into little cliques, all right, and dissociate from each other. So see how dissociate's not really that technical of a word. It just means breaking apart. So when a compound breaks apart into ions and water, this is called dissociation. So a particle of sodium chloride will dissociate into one sodium ion and one chloride ion. Why? Because the formula has NaCl has one sodium and one chlorine in it. All right? All right. This is not a shock, is it, that an ionic compound would break down? Now, the formula of magnesium chloride is MgCl2. For every one magnesium ion, there are 2 chloride ions. So that means when this is dissolved in solution, we have 3 ions. We have a +2 magnesium ion, we have a chloride ion, and then we have another chloride ion. So 3 ions from each compound particle. From each compound particle. Is dissociated. And of course, there are millions of these. All right. Yeah. But we're talking at the particle level when we show the beaker picture. And then what about AlCl3? It's also very soluble in water. And we notice that for every one aluminum ion, +3 ion, there are 3 chloride ions. So we'll put the aluminum +3, all right? And we know there's a chlorine. And remember, all the ions are going to separate, aren't they? All right? Why? Because each one is surrounded by water particles. So the aluminum chloride crystal was broken up by water particles who only take 1 negative ion with them and 1 positive ion with them. So that's why there are 3 chloride ions separately. So there are 4 ions from each AlCl3 compound particle. All right, let's see if there's any wisdom over here. All right, it says dissolving is a physical change. Oh, it's not a chemical change because we still have the same substances. We still have water, right? In salt water, the salt disappears after it's dissolved. However, we could still taste it. So we know that the salt is still there. All right? So, all right. I was going to say something else. How do we know if the ions are really there since we can't see them? Oh, well, the lab we do after this. I'm going to see if you become convinced that there actually are ions. All right, so let's write some simple equations for the physical change that occurs when an ionic compound dissolves. So here's an example. So I picked on aluminum chloride again since we already did it. So AlCl3, when it's dissolved in water, we put AQ after it. But really happens in the beaker, we know, is that we have that. Yes. what we really have is this. All right. Yes. When we put the aluminum chloride in, it immediately breaks up into these ions I'm telling you, but we haven't proved it yet. All right, so when we write the equation for this, we just indicate that it immediately dissociates. So what this is about is dissociating. All right. AlCO3 dissociates because those water molecules are tearing it apart. Yeah, because water molecules are tearing it apart. And we get one aluminum, and we don't get a Cl3, we get 3 Cl ions. That's maybe the most common mistake. So the ions are dissolved in water, so that's why we put AQ for aqua or agua after them. This is like a state of matter. You know, there's the solid, the liquid, the gas, and solutions are, when you have an AQ after this, it means that whatever you have here is dissolved in water. The correct formula for the ionic compound tells you the number of ions. So aluminum chloride has 1 aluminum ion and 3 chlorine ions. All right, let me show you again how we know that. Remember when we did this, we had aluminum, and it has 3 valence electrons. All right, and then we have, it has 3 that it's going to lose. All right, it wants to lose all of them. All right, so there's an electron out here now. All right, an electron out here and an electron out here. Well, we know that chlorine is going to go after it. So we're going to have a chlorine come in because it needs 1 more, right here. And another chlorine is going to come down here because it needs another one as well. All right, and that slips right in. And then we know another chlorine is going to come because it also needs another electron, and there it is. All right, so isn't it clear when you look at this that there's 3 chloride ions? Yes, so that's why we put 3Cl3 instead of a Cl. Let me fix this. Instead of a Cl3. All right. So remember I said that's the most common mistake people make. So the ions are all broken apart separately by the aggressive water particles. So that's how the crystal is broken apart and all the ions are separated. So each of these will be attacked. Each of these is attacked by water. All right, a water molecule is grabbing each of these, and pretty soon they're surrounded totally by water molecules, so water particles. So see how there's going to be 3 ions that are separated by the water particle, and then of course they're going to go after the aluminum plus 3 ion. And that's why we have 3 chloride ions rather than something like Cl3. Now I want to show you another example of a polyatomic ion. All right, I picked magnesium sulfate dissolving in water. So the first step is to write its formula, MgSO4, and we know that's correct, plus 2, minus 2. All right, and when it dissolves, it's going to break apart into the ions it's made of, magnesium, and the polyatomic ion. How do we know this? Well, polyatomic ions stick together in water. Stick together in water. We're going to find out covalent covalent molecules in water don't go together too well, except for the tiniest of them. Well, polyatomic ions stick together and do not break apart. They do not break apart. They do not break apart into sulfur and oxygen. Into sulfur and 4 oxygens. Partly because they're unlikely to form ions. So polyatomic ions are covalently bonded atoms together. They are not ions. All right, so these are covalently bonded.
Are you done recording?
I am, but you may speak to me just a second. Let me pause it. Let me see. So, Mr. Jones just came in. Okay, now, so these stick together in water, all right? Yes, the water surrounds them as a total thing. Now, what I want you to do is these 3 over here. All right, potassium iodide dissolves in water. Write the equation for this physical change, but you do have to write the first step. First, write the correct formula, okay, for potassium iodide. All right, and follow the example exactly as I did. It's just that instead of doing aluminum chloride, you're doing potassium iodide, but follow the same theme. All right, I want you also to get used to using the aqueous because it's kind of a state of matter thing. When you put aqueous after something, it means it's dissolved in water, which is totally different than it just being a solid, right? The second one is sodium sulfide dissolves. Write the correct formula and write the equation for the physical change following exactly what we did here. All right, then what I want you to do is answer these questions. I want a sentence or sentences with technical details learned in this lesson. All right, and then the last one, I want you to explain in sentences what's going on in this image. I don't want you to just label it because it's kind of already labeled. I want you in sentences to describe it. All right? All right, I'll talk to you later. Have a good day. Bye.